Is it just 2 people today? Okay. Okay, getting more. All right. I'll just text that it has started. All right. Okay. Not too many people. Yeah. Sorry, I was a bit ill last week. Still COVID positive. So yeah. But yeah, I feel much better. Anyways, I've got a few problems for you prepared for you today, and looking through the problems for physics. So today we're focusing on physics. I've noticed that the problem with the wire of variable cross section, that's actually a really difficult one. And let me know if you disagree with me. Maybe it was real easy for you. But I've done a very similar problem today, and let me share it with you. Okay, you should see my screen. If you don't, let me know. So we have find the resistance of a truncated hemisphere made of a material with resistivity ρ and radius r. The radius of the smallest circle is r. So it's a truncated semicircle. Basically, we took a metal ball, we cut it in half, we cut a little slab off the edge. If we don't cut off the slab on the edge, we're going to get some really weird results, as in the cross-sectional area becomes 0, so the resistance becomes infinitely large. So it's a whole mess down there. So I left it simple. So we have the left edge has radius. Has radius r, and this edge has radius r small. Just a second. Okay, now it should be better. And share screen. Here we are. Apologies. Find the resistance of a truncated hemisphere. Okay, so we are interested in this bit. So we're really not interested in what's happening here. So like this bit is completely useless to us. We just need the resistance. And we're going to use integration to do that. So you have a very similar problem. I think it's problem number 5 in the assignment. You have a y of variable cross section. So what I'm going to do, well, first of all, I'm just going to get rid of the unnecessary stuff. And I'm just going to stretch it just for the sake of it, because the picture is yeah. So I'm going to delete that. So I'm looking at it from the side. And first of all, well, I'll introduce some coordinates. So this will be the x-axis. This will be the y-axis. And because it's a circle of radius r, we can deduce that x squared plus y squared is equal to r squared. Therefore, y is equal to square root of r squared minus x squared. Good. So we've established that. So this is the radius. This is the equation of this curved line. Equation of this curved line. Right. The radius of the smallest circle is r small. Well, we kind of need to know how tall this is. How tall this is. And you know what? I'm just gonna modify this question. I'm just gonna simplify the maths here. The semisphere has height. It has height h. So what is h? H is this distance. Okay. I just made life easier for myself. Height h. So how does that work? We need to take a single slab. Let's say we cut the semisphere. We cut the semisphere into slabs, vertical slabs, and we take one of those slabs. So let's say we do it like this. Okay, so let's look at one of those slabs. So this is a slice of the sphere. Okay, so to find the resistance of this piece, we need the resistivity, of course. We need the length of this piece, and we divide by the area. So the length, we will use dx for the length. Dx is the length of the slab. So we're slicing it into very thin pieces, infinitely thin, in fact. The area is pi r squared, and r, we know it's this. So this is the radius of the slab. So the area, the cross-sectional area, is going to be, I'm going to write it here, is going to be pi multiplied by r squared minus x squared. So as you can see, the area of the slab depends on where we are along the wire, along the very weirdly shaped wire. And finally, we say that the resistance is not r, it's a tiny fraction. So it's going to be dr. Okay, so dr is going to be resistivity multiplied by the length, which is dx, divided by the cross-sectional area, which is pi r squared minus x squared. Now, as you understand, if we cut it into pieces like this, they are all connected in series. So the total resistance, the resistance of the slab, the resistance of the hemisphere, the total resistance, is the sum of all resistances, dr. In other words, it's the integral. We need to integrate this bit. We need to integrate this bit, and it's the integral of rho dx divided by pi r squared minus x squared. The variable of integration is x, so an x changes from 0 to h. And yeah, and that's the thing. So and then you just integrate to find the total resistance. Now integrating this is a whole other story. How do you integrate something like that? How do you integrate that? Okay, so what I'm going to do, on one hand, I do want to show you how to integrate this. On the other hand, I really don't want to confuse you too much, because the integral that you will be doing is much simpler than this. But yeah, I'll start, and if it gets too complicated, I'll let you know. But so far, how well do you understand what we've done on a scale of 1 to 10, as usual? Or maybe you have any questions, please let me know. Okay, lots of 10s, very nice. Lots of 10s. Nice. Anything confusing in particular? Okay. Right. So now we want to integrate this to find the total resistance, of course, because that's what we needed. So we take the rho and pi out, and also we take the -1 out. So it's going to be minus rho pi integral from 0 to h x squared minus r squared. But x squared minus r squared, it's x minus r, x plus r, 1 over that dx. Does anyone know what's the next step? Anyone have any idea? What's the next step? How to integrate this? Well, we want to simplify the expression. 1 over x minus r, x plus r. And I'm going to venture a guess that I can write this as a over x minus r plus b over x plus r, where a and b are constants to be found. Yeah, partial fractions, by all means. It is called partial fractions. Some of you might have done them. Some of you might maybe not. But we simplify this. We simplify this is equal to, we make it into one fraction. So x minus r. Remember, r is a fixed number, and x is a variable. X plus r. And here we get ax plus ar plus bx minus br. And the interesting thing about partial fractions that this thing, for any value of x, this thing must equal to this thing. So in other words, ax plus bx must equal to 0, and ar minus br must equal to 1. What do we get from here? Well, from here we get that a equals minus b, and so minus br is equal to 0. So b is equal to minus, sorry, not 0, 1, and minus 1 over 2r. B equals minus 2r, and similarly a is equal to 1 over 2r. So this can be written as, I hope I haven't lost you, minus rho pi integral from 0 to h 1 over 2r x minus r minus 1 over 2r x plus r. Okay, dx. And we can take 1 over 2r. 2r goes here, so we don't want that. And the integral of this, so it's minus rho 2r pi square brackets. It's a logarithm. It's going to be logarithm of x minus r minus logarithm x plus r and between limit 0 and h. And all we need is just to substitute. So this is going to be minus rho 2 pi r, in fact. And so we plug in h, so it's logarithm h minus r minus logarithm h plus r minus logarithm. Well, you plug in 0 and it's going to be logarithm r minus logarithm r. So it's going to be 0. So minus 0. And that's it. So we get the final answer. So it's going to be, we take the minus inside and it's going to be rho 2 pi r logarithm. I'm going to simplify it. I'm going to have a fraction of h plus r divided by, well, it's going to be logarithm h minus r, but h is less than r capital. So it's going to be r minus h. R minus, because it's a modulus. And we know that the modulus makes it positive. And the positive version of this expression is r minus h, because h is smaller than r. And that's it. That's the answer. I mean, it's not. So the hardest part of this question is obviously the integration, but the integration in the assignment is way easier. So you do the same principle. The only thing that is different in the assignment is the function. This is the only thing that is different in the assignment. And of course, well, here you have h. On the other, there you just need to find the radius r1 and r2. Okay, moving on. We have a circuit here, and I just want to show you a method of solving circuits. The question itself is quite mundane, but the interesting thing is how I will approach to find this. So here you need to find voltage between A and B. Voltage between A and B is also known as potential difference. So we need the potential difference. So voltage between A and B is also known as the potential at A minus the potential at B. Now, interestingly, if I put another point here, and I call it point C, obviously I can say that I can write that potential at A minus potential at C plus potential at C minus potential at B. So look at that. What I've done is I've artificially introduced potential at C. Okay, potential at C, and what I did is I did A minus C plus C. So these theoretically can cancel out, and you're left with the same expression. But instead of doing that, I'm putting this into brackets and saying potential at A minus potential at B. And look, potential at A is smaller than the potential at C because the current is flowing anti-clockwise. The current is flowing anti-clockwise, so we can say that if the current is flowing anti-clockwise, we go from plus minus here, plus minus here. This is plus minus. This is plus minus. So the battery always, well, the battery either increases or decreases the potential. So if we go from B to A, the battery increases the potential, whereas the resistor decreases potential. So phi A minus phi C, so potential at A minus potential at C, is going to be equal minus I, which we need to find, R2, minus I R2. Do you understand why minus? Or 1 for yes, 0 for no in the chat, please. Do you understand why minus? Because the resistor decreases potential along with the flow of the current. So if you go backwards, you go from A to C, you're increasing potential. So phi A minus, so the potential at C is greater than the potential at A. So therefore, A minus C is going to be a negative value. Okay, I hope that makes sense. I haven't received a reply from everyone. I mean, please never be shy to put 0 if you don't understand. Okay, so and now I am I do EMF, and EMF, and you can see because I'm going from plus to minus, it's going to be plus. Going from plus to minus, so the potential is increasing from C to B, and it's going to be EMF2. Now, do we have enough data? Well, we don't. We know R2, we know EMF2, but we don't know I. Okay, so to do I, we're just going to write out, actually in a similar way. I'm gonna make it a little bit more fun. I'm going to introduce a point D. Right. And I'm going to write down that potential at A minus potential at A is equal to 0, which is a very obvious statement. Potential at A minus potential at A is 0, right? But now I'm going to write it. It's a different way of looking at the Kirchhoff second law. So potential at A minus potential at D plus potential at D. Sorry, I'm being inconsistent with how I'm using the A's. So A, small a, of course, small a. Potential at A minus potential at A is 0. That's obvious. Obvious. So phi A minus 5D plus 5D. So here, I'm artificially, I can cross them out, right? They simplify. Then I'm going to be minus potential at B plus potential at B. Still being inconsistent with the capitalization. Then minus potential at C plus potential at C. And then finally, we get minus potential at A. And that's going to be 0 because all I did is, well, they all cancel out. But instead, what I'm doing is I'm doing this. All right. So potential A minus D. So we're going from plus to minus. Yeah, because the current flowing this way. So from plus to minus, so it's going to be IR1 plus. Now here we're going from plus to minus again. So it's going to be D minus B. So potential at D minus potential at B is going to be plus EMF1. Then we go from a B to C, and here we're going from minus to plus. So we are increasing potential. So basically, it's not a potential drop; it's a potential rise. So it's going to be negative EMF2, and C minus A. Finally, we're going from plus to minus again, so it's going to be plus IR2 equals 0. And now we have everything. So we can find IR1 plus R2 is equal to EMF2 minus EMF1. So the current is the difference of EMFs. So it's 1.3. So, well, okay, E2 minus EMF1 divided by R1 plus R2 is going to be 1.3 minus 1 divided by 10 plus 5. 10 plus 5. And the answer is 0.02 amps. 0.02 amps. And finally, we use this. We plug this into here. And now we have everything. Minus I. I'll explain, Edward. Just give me a moment. So I plug this in. And minus 0.02 times R2, which is 5, plus EMF2, which is 1.3, and the answer is 1.2 volts. So the potential difference between A and B is 1.2 volts. Okay, so how to make sense of the potential? Well, let's look at a simple example. We have a piece of a circuit. There's a resistor, then there's a lamp, and then it's connected to a battery, and then it's connected to the ground. The ground is always at 0 volts. This is the potential at the ground, 0 volts. Let's say the battery has EMF 10 volts. And this point on the circuit has potential 100 volts. 100 volts. This is the change. So this might be a bit confusing because here the battery is the voltage on the battery, is the potential difference across the battery. So the potential here is 0 volts. The potential here must be 10 volts. Now the lamp, so the current flows this way, because current flows from large potential to low potential, always. The current will flow this way, from large potential to low potential. So basically the current is charging this battery. So the battery it's working against the battery. And also, let's say the lamp has a voltage on the lamp is, I don't know, 20. So this would be 30 volts. And here, obviously, it's 70 volts. So let's call this point A. This is point B. This is point C. This is point D. So let's do phi A minus phi B. Is it a potential drop or increase? Are we losing potential as we go from A to B, or are we gaining potential? It's a drop, of course. And phi A is going to be 100 minus 30. So it's 70. So a drop is positive. If we're going from B to C, we're losing potential again. If we're going from B to C, you're going 30 minus 100, it's 30 minus 10. It's going to be 20 volts. So that's a loss. It's a loss. And if we go from C to D, so potential at C minus potential at D, well, oh. Okay, that's not what I wanted to do, sorry. Here, we're losing potential. What I meant is to put the battery the other way around. Let's say the battery is like this. So I have to change these slightly. Sorry. So this is EMF. Let's say it's 10 volts. But if this is 0, that means this has to be negative 10. Because the battery provides a potential difference. If there's no internal resistance, you always have the potential difference across the battery is the EMF. And if this is 0, and we know that the battery has 10 volts higher, so here is 1. Okay, maybe I'm going to do it. Okay, let's keep it this way. I don't want too many changes. Let's say this is 30. Okay, so this is 100 minus 30, which is 70 volts. That's a loss, and it's positive. And 30 minus 10, that's 40 volts. That's a loss again, and it's positive. And the battery, we're going C minus D. So it's minus 10 minus 0. So it's minus 10 volts, and that's a gain in potential. So the gain is negative, and the drop is positive. Basically, I think the short answer is that phi I minus phi B is the drop of potential from going from A to B. So if the drop is positive, that means it's a gain. Okay. Does that make more sense? Or did I confuse you even more? Okay. Okay, so this one. Now here you can, there are different ways you can do this question. So we know all the resistances except this one. R is unknown. So it does say R is unknown. This one. However, we do know the current, and we need to find the voltage on the voltmeter. The thing is that if you knew the resistance, that immediately you know everything. Okay. So what I'm going to do, I'm going to simplify my circuit. Well, first of all, 10 and 15. If you have 10 and 15, the combination is, who is very quick at calculating? Who can tell me the answer? What's the total resistance? It's a parallel combination of 10 and 15. Very close, Adam. Thomas, yes, you're correct. 6. Adam, you forgot to take the reciprocal. It's 6 ohms. It's a very common mistake, so please do look out for it. People forget it. And which makes sense, 10 and 15, so the total must be less than 10, not dramatically less than 10, but less than 10, which is 6, which makes perfect sense. And let's look at this combination. This is a combination of two batteries. And we know that a parallel combination of 2 batteries has the same EMF. However, the total resistance is going to be half because they're in parallel. So I'm going to draw an equivalent circuit, less neat, but equivalent. And it's going to be a battery with the same EMF, but half the resistance. Then there's going to be this battery, which hasn't changed. Then we have the ammeter. You don't have to draw the ammeter. Then there's going to be a resistor of 6 ohms. And there's another resistor, which we don't know. And like this. But now we have two batteries in series. And 2 batteries in series, we know that the resistances and the EMFs add up. So the total EMF is going to be 2 EMF, 2E, 2E. And this one, this is R over 2. It's supposed to be R over 2. And the total resistance is going to be 3R over 2. 3R over 2. So in other words, so EMF is what? EMF is 1.6. So this is going to be 2 times 1.6, it gives 3.2 volts. And the internal resistance, so internal resistance 0.8. So 3 times 0.8 divided by 2, that's going to be 1.2 ohms. So we've simplified our circuit very much. And now we just need to write down the equation. So current is equal to EMF divided by the total resistance of the circuit, which is R plus 1.2 plus 6. Sorry, 2 EMF. So it's 3.2. Well, 2 EMF. So it's 3.2 divided by R plus 7.2. And we know the current is 100 milliamps, which is 0.1 amp. And from here, we get R, 0.1 R plus 0.72 equals 3.2. R is equal to 3.2 minus 0.72. And then times 10 is going to be 24. 24.8. 24.8 ohms. 24.8 ohms, and we know the current. So the voltage on the voltmeter, voltage is going to be IR, which is 0.1 times 24.8, and it is 2.48. 2.48 volts. And then a sanity check. Does this answer make sense? Well, it does. So this is 6 ohms. The voltage is, so the total resistance is around 30 ohms. Does that make sense? So if you have 3.2 volts of EMF and in the 30 volt resistor, the current is going to be around approximately 0.1 amp, which makes sense. And then the voltage on the resistor must be between 0 and 3.2. So it is 2.48. So yes, so I'll just write sanity check. Sanity check. Okay, any questions here? All right. Remember, batteries in parallel, if they are the same voltage, that doesn't change. The voltage doesn't change. If they're not the same voltage, then it's super complicated. What do we have here? Okay, so now I was trying to do this question before the webinar, but honestly didn't have enough time. But I'll do it with you. If I get stuck, then just yeah, we'll leave it for a better time. But hopefully not. So what do we have here? We know that the resistors are the same and the resistances are. We know that EMF1 is EMF, EMF2 is 2 EMF, 2 EMFs, and EMF3 is 4 EMF, 4E. Basically, if this is 1 volt, 2 and 4 volts. Okay, so what can we do here? Well, we need some currents. We need to write down the currents, and there's, well, you need the current in each of the branches. So what are you going to do about it? Now this is, let's call this I1. Let's call this I3. I'm going to call this I0. I'm going to call this I2. Now, I assume the current in here flows this way. So I'm going to write it down. So I0, I1, I2, I3. We have 3 currents already. Then we have I I4. And here, well, I assume the current would flow this way in this segment. So I5. Okay, so 6 different currents: I0, I1, I2, I3, I4, I5. Not great, but doable. So the first thing, for the first junction, I can write that I0 is equal to I1 plus I3. In a similar way, because I0 is here, I0, I2 is equal to I0 plus I5. So this is using Kirchhoff's first law. So currents flowing in, currents flowing out. So currents flowing in equal currents flowing out. Then we have 2 more junctions. So I3 plus I5 is I4, and I1 plus I4 is equal to I2. Right. Okay. Now let's use the same approach. So I'm gonna call this A, B, C, and D. Maybe C and D. So rather than using the Kirchhoff's laws directly, I'm going to use my new method of potential differences. So let's start. So phi A minus phi B. Phi A minus phi B. You can write it as phi A minus phi C plus phi C minus phi B. Okay. So phi A minus phi C. So that's I1R. And phi C minus phi B, this is I2R plus I2R. Okay, not so bad. On the other hand, we can write that phi A minus phi B is phi A minus phi D plus phi D minus phi B. We take this, and this is phi A minus phi D is I3R, and from D to B, because we're going from plus to minus again, so we are decreasing potential. So it's going to be plus EMF2. So there's going to be 2 EMFs. All right, and because of that, I can write, joining these two together, that this is equal. These are equal. So I3R plus 2 EMFs equals I1R plus I2R. Okay, now phi, what else can I do? I can also say phi A minus phi B. Phi A minus phi B is EMF3. EMF3, which is 4 EMFs. If I go from A to B, it's 4 EMF. And if I go, and I can also say that phi A minus phi B And let's do the difficult route. It's phi A minus phi D plus phi D minus phi C plus phi C minus phi B. So now we have 3. Those of you who are attentive, you will see that this is no different from the Kirchhoff's second law. I'm just doing Kirchhoff's second law in a slightly different way. A minus D is going to be I3R, then D minus C. Now here we're losing potential. We're going from minus to plus. We're gaining potential. So it's going to be negative. It's going to be negative EMF plus C minus B. So it's I2R plus I2R plus I2R. And once again, they're equal. So this is equal. This is equal to that. So from here, I got 4 EMFs equals I3R. So what did I miss here? I1R, I3R, and I3R minus EMF plus I2R. Is that helpful? Well, yes. 5 EMFs divided by R is equal to I3 minus I2. And here we have 2 EMFs divided by R is equal to I1 plus I2 minus I3. Ooh, I am extraordinarily lucky here. Would you look at that? And this is a complete coincidence. If I take these two equations and I add them, I immediately get I1. And to do these questions, you need a lot of practice because you need to spot these things. And so basically, this is a simultaneous equations with 6 unknowns. Yeah, there are 6 unknowns: I0, I1, I2, I3, I4, I5. And when you start noticing these things, oh wow, so it's 7 EMF over R is equal to I1. And this is just me being very lucky. I mean, I could have spent another half hour just solving that. And that makes my life so much easier because now I can find, I can choose, okay, so I found I1. So what can I do now? I1, I1, we just need to find an equation which contains I1 and another one, but only 2 different currents. So I1, oh, of course. So phi A, so sorry, just zoom. So here, I'll write it down here. So phi A minus phi A equals phi A minus phi C plus phi C minus potential at D plus potential at D minus potential at A. So we're doing this, this, okay. And phi A minus phi C. So if A minus C, that's I1R, plus C minus D, that's EMF, and D, that's phi D minus phi A. So because we're going from minus to plus, we're going backwards. From D minus A, we're going backwards. So it's going to be minus I3R. And the whole thing is 0 because phi A minus phi A is 0. And finally, we get I1 minus I3 equals minus EMF over R. So from here, I can get I3 is equal to I1 plus EMF over R. And I1 is 7 EMF over R plus EMF over R. It's 8 EMF over R. That's I3. That's going to be useful. And then we just we literally just go ahead and find I2. So I1 is 70 over this. So I2 is going to be I3 minus 5 EMF over R. So that's 8 EMF over R minus 5 EMF over R is going to be 3 EMF over R. Okay, so we found I2, 3 EMF over R. Then we need to find I. Then we go here. So I0 is going to be I1 plus I3. So I1 is 7, I3 is 8, so 15 EMF over R. Okay. Feels a little bit weird. It seems like, why is it so big? I0. Oh, we'll see if it makes sense. Then we have I5. I5 is equal to I2 minus I0, which is here. I'm using this equation. So you just have a bunch of equations and you need to solve them. So the hardest part is finding the first unknown current. Once you have the first unknown current, then it becomes very easy. So there are a few questions like that in the assignment where you need to use that. And one of these questions is where you have a network of resistors with 5 different resistors, and you need to find the total resistance. So I5 is I2 minus I0 So that's going to be I2 is 3 minus I0, so it's minus 12 EMF over R. So interestingly, we did not guess the direction of I5 correctly, unless they've made a mistake somewhere. We'll see if it makes sense. I5 and then I4. I4 is I3 plus I5 plus I5. So I3 is, where is I3? I3 is 8. I5 is minus 12. So it's minus 4 EMF over R. Okay, so we found everything. We found everything. Just a second. Yeah, so that's how you solve it. You write down all the equations and then you try to figure it out. Just need to be very careful. And there's a few more questions. I'm thinking which one is the most interesting one. Okay, 5. We'll skip 5 for now. Find the current in the battery. So problem 6. So this is an example where you don't really need to do where you don't really need to well you could use Kirchhoff's laws, but in fact you can use equivalent circuits. So you have two resistors here, and we know that parallel resistors is R over 2. Okay, so this is R over 2. And R over 2. Let's see if I can make it. So R over 2. Then we have R and R over 2. So that's 3R over 2. Over 2. So R and R, that's 2R. 2R. 3R over 2 and 2R. Okay, so we can use the shortcut formula. So it's going to be 3. So R1, R2 divided by R1 plus R2. That's the total resistance of two resistors. A very useful formula. And using this formula, you will very rarely forget to find the reciprocal. So it's 3 over 2R times 2R divided by 3 over 2R plus 2R. So that's 3 over 2 plus 2. So which is 4 over 2, which is 7. 7 over 2. So that's 6 over 7. 6 over 7R. Okay, so this combination is 6 over 7R. So we are left with R, 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 R. Then we have R, and we have 6/7 6/7 R. Really hope I didn't make a mistake. I'll just double check. 1/1.5 plus 0.5. 6/7, yeah, indeed. 6/7. And like this. And this is R. Or in other words, it's 3R. So that's 3R. And this is not this is R plus 6/7R. So that's 7/7R plus 6 is 13/7 R. 13/7 R. So we need to find the total resistance. So it's going to be 13/7 R times 3R divided by 13/7 R plus 3R. So that's 39/7, 39/7 R. And this 13/7 plus 1 is 21, 13 plus 21, 13 plus 21/7. Luckily 7 cancels. So we get 39 over 34R. Okay, and plus 1, so it's 39 plus 34. The total resistance is R plus 39 over 34R, which is 73 34R. And the numbers will tell us whether whether it is whether we did it correctly. And it looks like because in the question R is 34, so the total resistance, so 73 over 34 multiplied by 34 ohms, it's 73 ohms. The total resistance of the network is 73 ohms, and we need the current, and we need the current in the battery. And the current in the battery, of course, is the EMF divided by the total resistance, which is 7.3 divided by 73, which is 0.1 amp. Okay. Good. So that's it. Yeah, that's the question. Right. A wire is made of wire made of nichrome, and resistivity is 1 micro-ohm meter. Cross section of the wire is 1 square millimeter. The radius, the internal resistance of the battery is 1.5 ohms. The EMF is 2 volts. Radius of the circle is 1 meter. Find the voltage between C and D. So quite an interesting setup here. You need to find the voltage between A and B and C and D. Okay, so to do this, we will first direct the currents. Well, it's quite obvious that the current goes this way, and here the current goes this way and this way. And then the currents come back and back here. More to that, these two currents have to be the same because it's because of symmetry. So this is I1, and this is going to be I0, because why not? Cool. Now we need to find the resistance of each branch. So to do this, we're going to redraw this circuit. So I have a battery with EMF and internal resistance R. Now, each of these wires has half the length. So we know the formula for resistivity. Resistance is rho L divided by cross-sectional area. Okay, so the equivalent circuit for this would be like this. So there's a wire here, there's a wire here. So these represent these branches, because this wire and this wire. So these two represent. Now, that's going to be confusing, so I'm just going to use this. Well, let's call it R1 and R1. This is R1 and this wire is R1 because they have the same, it's in the middle. Now the top wire, let's call it R2. The resistance of the top wire is R2. And we have R2 on the bottom, R2. But we also have R2 on the top. But that simply means that it's also in parallel. In parallel, R2. So R1 is the resistance of this length of wire. R2 is the resistance of this length of wire. Do you understand how these two circuits are equivalent? Do you fully understand how these two circuits are equivalent? Please give me a vote from 0 to 10, as usual. From 0 to 10, do you understand how these two circuits are equivalent? Brilliant. Right. Very nice. And because these two resistors are the same, well, why not just write R2 over 2 and forget about this bit? Because they are R2 over 2. And we only need the current through the battery. So we're not interested in the bottom current. So we are really not even interested in this current. We only need the current in a circuit. So we've reduced the circuit to this. And all I need now is to find the current. Oh, sorry, I need the voltage. Okay, but first we need the current. Current, let's let it be I0, is the EMF divided by the total resistance of the circuit. The total resistance of the circuit consists of a few things. So it's going to be R1 plus the internal resistance plus another R1, but we'll just write it here, and plus R2 over 2. R2 over 2. All right. And that's all we need, basically. Now we just need to find R1. So R1 is the length of the wire. So that has length A over 2. So I'm going to write it here. So R1 is resistivity multiplied by length, which is A over 2. A over 2, that's the radius, half of the radius, divided by cross-sectional area, which is A, which is given. So it's going to be 1 micro ohm meter. I'm going to be very careful with units on this one. Multiplied by A over 2, so it's 0.5 meters. And now 1 square millimeter. 1 millimeter squared. Interesting. The thing is that 1 millimeter squared. So I'm just gonna 1 millimeter squared. It's, well, it's 1 times 10 to the minus 6 ohm meters times 0.5 meters divided by 1 milli squared is 10 to the minus 6. So 1 times 10 to the minus 6 meters squared. And interestingly, everything cancels, and we're left with 0.5 ohms. Nice. 0.5 ohms, that's R1. And now we need to find R2. R2 is same thing, rho times, no, the length is different. So it's going to be 0. So the length of R2, that's pi R, pi A. Oh, yeah, that's it. Pi A divided by cross-sectional area A. Now, nothing's changed here, so this one sort of cancels out with this one, and it's going to be pi ohms. Now, in physics, we don't usually put pi ohms here, so it's going to be 3.14 ohms. And that's what I need to plug in here. So EMF is 2 volts. 2 volts divided by 2R1, so that's 1 ohm, plus internal resistance, which is 1.5, plus half of R2, so it's, well, pi over 2. Pi over 2, which is 1.57. 1.57, and that is roughly 2 divided by 1. 0.49 amps. Okay, and now we need to find the voltage between C and D. So voltage between C and D, it's equal to the potential at C minus the potential at D, which is, now we're going from left to right, so the current is flowing right, so it's going to be plus I0 R1. Now the battery increases potential, so it's going to be minus EMF minus I0 R, and it's going to be minus, plus I0 R, and it's going to be plus I0 R1. Do I need to do that? Yeah, I mean, it's not super dramatic. So you can see between C and D, I'll just draw them here. Between C and D, the current is flowing this way, and the current, we know the current is I0. It's like that. So all I need to do is just plug in the numbers. So I0, which is 0.49 times R1. R1 is 0.5. Oh, so there's 2 of those, so we can just write 2. So 2 times R1 is 1 times, so 0.49 volts, minus EMF minus 2, plus I0R. So it's 0.49 times 1.5 times 1.5. That is 0.737. 0.737, and that's something. 0.49. 0.49 minus 2 plus 0.737. Minus 0.773 volts. And now a bit of an existential thing. Like, how come it's negative? How come the voltage is negative? Well, because you're going from C to D. The potential drop is going to be negative because the battery increases the potential. So potential drop is negative. Potential drop is negative as the battery increases the potential. But the current is flowing from C to D. And before, several times, I said the current goes from high potential to low potential. But here we see current is flowing from low potential to high potential. So how does that make sense? Can somebody tell me? Let me know if you understand the collusion. The collusion here, that current goes from C to D. But we know that current goes from high potential to low potential. Here it's flowing from low potential to high potential. Is there a collusion, or am I thinking things? It's a very simple explanation. Too complicated? Flows the other way. Well, it doesn't. We have a current and it's positive, so the direction was correct. Can you elaborate on this, Edward? I think you're onto something. You just
like the current's allowed to flow in the wire, so it's allowed to go from D all the way. It's allowed to flow that way.
You mean around?
Yeah.
In the top wire? Yeah, of course. It's I'm just trying to trick you, looking at it from the wrong side of things. Current naturally goes from high potential to low potential, and it does go. It goes from D to C. It goes from D to C because current naturally goes from high potential to low potential. Yeah, so it's high, low, low. And so it is flowing from D to C. There's nothing wrong with it. This does not apply to batteries. Batteries change the way current flows. The batteries are allowed to push the current. The battery pushes the current from low potential to high potential. And that's what it does. It changes the potential energy of the electrons so they can later do work. So what the battery does, it raises the potential of the electrons, of the charge carriers, so they can later perform work going from D to C. So current does go naturally from high potential to low potential, but batteries are unnatural. Batteries do the opposite thing. Batteries give you energy. It is natural to lose energy. It is not natural to gain energy. Yeah, gaining energy is unnatural in the universe because you tend to lose it rather than gain. Okay, hope that makes sense. Now I can comment on the problem number 5. Number 5 is similar to some of the problems. It is certainly similar to this one because you'll need the lengths. I don't have time to do the whole thing, but we need the resistance between points A and B. So what you do is you connect an imaginary battery. You connect an imaginary battery here. Let's say you could use a voltage. Why not? I'm just going to use EMF, but you could say it's a 10-volt battery. Yeah, there's nothing wrong with it. The battery of EMF. So there's a current here. Let's say it's I0. Now here, let's say this current is I1, and this current is I2. And because it's symmetrical, this is also going to be I2. Now here, current can choose to go this way, or it can choose to go up. But also when I2 reaches this point, it can choose to go down or choose to go straight. So just for the sake of it, I'm going to assume that the current is flowing this way. So I'll call it this I3, and I call this I3. Now this current goes I4. Well, instead of writing I4, you can straight away write down I1 plus 2I3. I1 plus 2I3. I like to have fewer variables, and this one is going to be I2 minus I3, because I2 is coming in, some current is going here, and this is going to be I2 minus I3. Same here, I2 minus I3. And again, so this is I0. So I can do with 4 currents. Dealing with 4 different currents, so 4 different variables is acceptable. But earlier you saw me dealing with 6 different currents, and it worked, kind of accidentally. But I mean, it's just sometimes it takes a long time to get there. And here, so the resistors. There are 2 types of resistors. There's the AC. Let's call this R1. So this is R1, R2, and this is R1. So R1, 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 and this is R2. This is R2, and this is R2. And of course, you can find R1 and R2 because you know the radius of the you know the radius of the circle. This has a radius R. Okay, so what can we do here? we go phi A, well, EMF, or yeah, because we eventually need to find I0. So the total resistance is going to be EMF divided by I0. This is what you're looking for. And all you need to do is just express, you need to find I0. I0 is the thing that you're looking for, and it will be expressed in terms of EMF. So EMF is going to be equal to phi A minus phi B, which is I1 R1 plus this current, so I1 plus 2I3 R1 I1 R1, and then you do it another way. So EMF is 2I1 R plus 2I3 R. Interesting. I1 plus I3. I1 plus I3. What is I3? Is that? Did you deduce anything from that? Well, not yet. Anyways, you carry on. You do AC minus phi A minus phi C minus phi B, and you aim in this question to get so find I0 find I0 in terms of EMF epsilon, and then you plug that in and you get the answer. Okay. Right. So let's finish here. Any questions? Any questions that you have for me? Anything you'd like me to go through briefly? What do batteries actually do to the electrons? Well, it's a chemical process in which well, basically there's a chemical reaction which pushes positive charges towards, or positive ions towards the positive terminal of the battery, and negative charges towards the negative ions towards the negative terminal. Well, if you think of like a lemon and two bits of metal, and you plug the two bits of metal into the lemon, the lemon acts as an lemon acts as an electrolyte, so it can carry charges across the two metals, and across these two metals, it is more likely that the electrons will be deposited on one metal, and the positive ions would be deposited on the other one. So it's carried by ions inside the battery. So like physically, it's not moving. It's not moving electrons. It's moving ions, and ions have either have an extra electron, or they're missing an electron. If they're missing an electron, they're ready to get an electron. So the positive ions get to the positive side, negative ions go to the negative side, and they create a potential difference this way. And once you run out of chemicals, you have the battery is dead. Battery is flat. All right, anything else? All right, then I'll see you next week. So remember, maths and physics are both due this Sunday. So we gave you some extra time, and we're preparing assignment 8 for you. You're welcome. See you.